Hello, everyone. We are Group Stargate, and welcome here. So today, Boshan, Shang, and I are presenting our final Capstone project, which is Stargate towards DynamoDB compatibility for Cassandra. We are advised by Jeff, Tatu, and Pravat. And now let's begin the presentation. So today there are many choices of databases, and the company can choose a database for their needs. So at one time, the company may choose one database, but maybe later they decide to change. But switching from one database to another is very difficult because databases, they have incompatible APIs, and for one database, they may not have the functionality for the other one. So if users really want to switch to a different database, they need to refactor the code base, and they also may be facing the problem of missing functionalities. So our goal here is to develop a middle layer that allows users to switch databases without refactoring the code. In this project, our focus is on DynamoDB and Apache Cassandra. Let's say users want to replace DynamoDB with Apache Cassandra. Because the Stargate and Cassandra do not support DynamoDB APIs, and DynamoDB is closed source. We aim to achieve in this project, we have this, we want to extend the current Stargate project so that it can receive DynamoDB API requests, but instead interacting with Apache Cassandra, and so that the user can feel like they can use the old code they use for the DynamoDB, but actually they are interacting with Cassandra. So the proposed solution here is Stargate. So Stargate is a data gateway for Apache Cassandra. They have REST APIs, document APIs, gRPC, CQL, and GraphQL. Our extension is to add a DynamoDB API plugin for Stargate so that it can also deal with DynamoDB API request. So the scientific hypothesis here is, so although DynamoDB and Cassandra, they have different implementations, they are both NoSQL databases, and we can use one to achieve many of the functionalities for the other. And also, if we can make the middle layer able to receive DynamoDB requests and send in DynamoDB results, the users can have keep the current code base while changing the underlying database, because they can still send DynamoDB requests and receive DynamoDB results, but they are actually interacting with Cassandra instead of the DynamoDB. And the API compatibility can be tested easily. We can just run the same piece of code on DynamoDB and Cassandra, and then compare the results for different databases. And for this project, our performance benchmarking is measuring the latency for both methods. So major feature here is the DynamoDB. So we want to extend Stargate so that users will send a DynamoDB REST API request to Stargate. Stargate will receive the request, translate it into the corresponding Cassandra request, and then send this request to Cassandra cluster. And once it gets the results back from the Cassandra cluster, it will translate the results back to the DynamoDB format and return the results back to the clients. So the intended user for this project are the existing DynamoDB users who want to migrate to Cassandra without large refactoring or rewriting of the code. And for the system functionality here, we want to achieve the same functionality that DynamoDB provides. So that's so for this API, we want to convert an incoming DynamoDB request to a Cassandra request, and achieving the same operations here in the underlying database and return the same result back to the user. For example, we now have the create table API, delete table API, and delete item, and many other APIs. For the non-functional requirements part, we have the performance requirements, scalability, and modularity. So for performance, is not a major concern here because we just started this project, and the correctness is our first priority, not the performance. Maybe in the future work, performance is an priority, but not for it now. And scalability is also not achieved very well now, but is also a future work. And for modularity, so within this DynamoDB module, so each endpoint is separated, and the DynamoDB adapter is can be separated from Stargate as a plugin. So the modularity is achieved here.
Thanks. So now let me quickly introduce our design in a high level. So this is our system architecture. We adopt a simple 4-layer architecture. Let's go from the bottom layer to the top layer. On the bottom layer, you see Cassandra. This is the real database that we are using. It's the actual database that executes all the queries and persists the data. And on top of it is the Stargate layer. It's called coordinator, but for now we don't need to know what coordinator means. Basically, it's a middle layer that establishes the communication between our adapter and the real Cassandra database. It dispatches requests and returns a response back. And our adapter has 2 layers, web service and proxy. The proxy layer is a main layer that handles every business logic. It needs to transform, it needs to parse it, it needs to transform and parse the DynamoDB queries and convert them into a Stargate intermediate representation and send to Stargate. On top of it is web service layer. And because DynamoDB server provides an HTTP interface, a REST API interface, we need to provide a similar interface so that the DynamoDB clients can communicate with. We provide RESTful APIs that are fully compatible with DynamoDB. We implemented many APIs, and this is one typical example of how a sequence diagram for an API would look like. Let's focus on the right part. You can see there are actually 3 round trips showing on the figure. We can see from the proxy, item proxy to the Cassandra node. You can see there are 3 round trips. So put item API itself is simple. It just inserts a new row to the database. But due to the difference between DynamoDB and Cassandra, specifically DynamoDB is a schemaless database, while Apache Cassandra enforces a schema. So in the worst case, we need to fetch the schema from the backend, alter the schema, and then insert the real data. So at most, it can take 3 round trips. But because of the cache we are using, as long as there is no frequent schema changes, it's going to be 1 round trip. So our deployment model is meant to be designed to be easy to use by the users. We ship container images so that users can deploy them as containers either on premise or on cloud. Actually, we tested both on our own local laptops and on AWS EC2. So this is a demonstration of the Stargate system as a whole. And Stargate already supports REST service, GraphQL service, Docs API, and a few others. And we are adding a new microservice to the Stargate ecosystem. Our risks can be categorized into 3 types: business risk, product risk, and process risk. The business risk is a main risk we are facing. How reluctant are users to migrate their existing business? This is a bit out of scope of this project, but we already see some users creating some issues on GitHub requesting a DynamoDB feature for Stargate. So we believe there are potential users for this. Product risks include how seamless the migration process would be. As we will show you in a simple demo, it's going to be really smooth and easy. Can we offer same quality for all use cases? This is ambiguous because we are still in the development phase. Although we have shipped an MVP, a minimal viable product, it is unsure that whether we will be able to cover 100% functionalities provided by DynamoDB. Process risks involves the lack of documentation and the closed source nature of DynamoDB. There are some corner cases that is not documented, and we are just not sure what the correct behavior should be. The major tools and dependencies include DynamoDB Java SDK. Of course, we need it because we need to let our server communicate with the DynamoDB client. We use gRPC, remote procedure call, that establishes communication between our adapter and the Stargate coordinator. We use Quarkus because we need to provide RESTful service. We use Antler because we need to parse the DynamoDB request. And Antler is a state-of-the-art parser generator that helps us generate parsers.
Yeah, so here I'm going to talk about a few about the revision of our plan for this year. So as you can see here, it's our roadmap for the Capstone project, and it roughly divided to two paths. The first one is the documentation works, and the second one is the development works. And what we have done this fall semester are marked as red boxes. So basically for the development works, last year, what we completed is dive deep into the Stargate source code and figure out the comparison between the two databases. One is DynamoDB and another is Cassandra. And so what we have done this fall semester is to implement the adaptation development for the Dynamo APIs, include those kind of APIs. And also what we have done is we merged the updated Stargate V2 version into our main branch, so we keep up with the latest functionalities. And we also make a demo for our Capstone project, which is a DynamoDB adapter. Beside from it, as for documentation work, this semester we have finished the final report. And we also made a proposal to the Cassandra Summit, which is a summit for the topics and discussion about the Cassandra database. And hopefully we can give a talk about it. So those things conclude the end of our project. So the results, the first result I want to share is about the database feature mapping, which is to unravel the differences between the two databases so that we can implement our APIs better. And as you can see, there are two tables here. The first one is the DB component comparison, and another one is the data type comparison. Most of the component and data types are similar, and there are only differences in the naming, but still there are a little bit about differences. For example, if you look at the table 2, and there's the list that existing in two databases, but the truth is actually the list in the Cassandra database, it does not support the nested list. So what we have to do is to eliminate that kind of difference by just making the nested list as binary form and put it into the original list. So that's how we handle that. And the same rules applies to the other differences. We have to eliminate that so that user won't feel any difference when using the database. Yeah, so after figuring out the mapping and comparison, we launched the API adaptation development. As you can see, here are all the APIs that we have completed. The first column is original requests or API from DynamoDB. And the second column is CQL statement of Cassandra database. So that's the most similar statements that we found out to complete the functionality of DynamoDB. So to trigger that statement, we need to use the function calls that are provided by the Cassandra SDK in the third column. So so that's basically how the logic is handled in the Stargate layer. So it's very difficult to complete this all kinds of APIs, and we do met a lot of difficulties and have to sacrifice a lot of things. For example, the performance. As for one of the API, which is put item API, actually, as you can see in the second column, it's very easy, seamlessly to the Cassandra database to just insert something into the database. But actually, for Cassandra database, it's not as seamless as DynamoDB does. So what we have to do is to, for example, if the user, he or she wants to insert a new column or new column or delete some column, we need to actually change the schema from the original schema and create a new one. So that actually we have to do a sacrifice from the performance. Yeah, so here is the performance test. Although we have stated that performance is not something that we are pursuing right now, we first concentrate on the correct and the consistency of the functionality, but performance is also something that we want to see if it is comparable to the original DynamoDB. As you can see in this table, the first two rows, as for first two rows, the table operations, the Stargate latency does better than the DynamoDB. One reason is DynamoDB table operation is asynchronous and is only roughly estimated to be done in 10 seconds in the backend. So I don't know, maybe Cassandra is really good in this part. But as for the other requests, as you can see, Stargate is not that, the latency is obviously a little bit higher than the DynamoDB's latency. But still is comparable somehow. So I think there are two reasons behind. The first reason is, as I have mentioned before, the Stargate, when we implemented that, because we want to keep the consistency, we have, make the user feel they are really using the DynamoDB. We have to do like 2 or 3 round trip time in the backend, triggering a lot of queries in the backend, so that sacrifice a little bit for the performance. And another example, and another reason behind is for the DynamoDB, we actually don't know how strong that AWS put that database on the machine. So if that machine is powerful enough, is of course we are not we are not able to compare with it. But as for the Stargate layer, we actually running on the EC2 instance. So I think that might be one reason that it costs more latency. Yeah, so here are also some resources that we have contributed. The first thing is, of course, the Cassandra DynamoDB adapter, which includes the source code, the Docker image, as well as the demo video in the link, and also the proposal that we submitted to the Cassandra Summit, and hopefully we will give some talks. And also we have posted a blog introducing our project on the Stargate website. And also we have give an internal talk in the data stacks. Yeah, so basically that's some contributions that we did other than our project.
So for the future work part, there are still remaining APIs to implement. So for example, the batch write item API and the scan API. So this is definitely one part of the work we want to continue. And also there are some APIs that are complicated to fulfill its full functionality, like put item API and update item API. And we hope that we can complete the full functionality of this. And also, as Sean mentioned before, and you can see from the results, some API, the performance are not very satisfying, and we want to improve the performance of some existing APIs. And also, we still need a way for comprehensive testing and benchmarking, because right now we only have the latency testing. And here are some terminologies for the project. and further reflection on what we've learned so far. So from the beginning of this project, we know nothing about DynamoDB and Cassandra, but now we are able to deliver some results of it. So that's a good thing. And also, in the beginning, we are working on the giant Stargate repo, and now we separate our part into a separate repo, which teaches us how to doing development work, and this also make developing more convenient. And also we learned how to use CI/CD and Quarkus and Docker for deployment. And finally, we learned how to collaborate within the teams. We how to divide and split and assign work to different teammates and communicating with each other. And that's all.
Cool. So we still have a couple of minutes left. Let's watch a demo from an example project we created. So we created this demo example project that showcases our plugin, our adapter, open source on GitHub, and we have a demo video available.
Welcome to the demo of Cassandra DynamoDB adapter. The adapter aims to bring about DynamoDB APIs to Apache Cassandra. The adapter is plugged into Stargate, a middleware that is capable of serving different APIs on top of Cassandra. This is the adapter repo, open source on GitHub. It contains the source code and user guide on how to launch the adapter. Let's follow the guide. We first need to launch the software. We have provided a Docker Compose script, and we have already launched the software using Docker locally. We launched the Cassandra cluster with 3 nodes together with a Stargate main component called coordinator and a DynamoDB API adapter. Using a Cassandra shell, we can see we have an empty database. We have no key space except the default generated ones. Next, we need to do authentication and fetch a security token for Stargate. We can copy the command and run in our terminal. It returns an authentication token, which we will need later. Next, we need to create an empty key space in Cassandra. The key space in Cassandra is like a namespace. This leaves space for multi-tenancy support in the future. Let's copy the command and run it in terminal. We need to replace the Cassandra token placeholder with the token we just generated. It successfully generated a new key space named DynamoDB. It doesn't contain any table right now. Cool, so we have finished configuring our cluster. Now let's take a look at the demo project. We open our demo project in JetBrains IntelliJ. This project is also open source on GitHub. It's a simple application that connects to Amazon DynamoDB, creates a table, writes some simple data, and query them back. Let's see the runtime configuration for this program. We set the AWS access key ID so that the DynamoDB client can connect to the DynamoDB on AWS. Let's run the program. It needs to sleep for 10 seconds because the table creation is asynchronous on DynamoDB. So it finishes creating the table, writes some data to the table, and queries them back. Let's go to the DynamoDB web console to see the changes. You can see a table generated, and we can see the 2 rows we just inserted. Now let's assume the client, the user, wants to migrate to Apache Cassandra. It's pretty simple. Since our Cassandra cluster runs locally, we need to pass in the address as program argument. In this case, the address is the local host. Remember the token we just generated? We need to paste it here. Note that even though the variable name is still AWS Access Key ID, it's not going to be received by AWS DynamoDB. Rather, it's going to be intercepted and used by our adapter. Cool, that's all. You don't need to change a single line of code. Now let's run this Cassandra demo. It doesn't really need to sleep for 10 seconds, but since we didn't change the application code, it still tries to sleep. It succeeds as well. Let's go to the SQL shell. We can see a crude sample table is generated. We can select the data. We can see the update time. Cool.
Yeah, so this is the end of our demo, and thanks for watching. We are happy to answer any questions.
Hey, nice job, guys. Really nice presentation. I think the first thing that comes to mind for me is if you could say a little bit more about how you had to organize to make this happen, right? So presumably, you know, there were certain best practices you were expected to follow with what you wrote that became part of this ecosystem, right? And you hinted at that a little bit in terms of the containers and so on that you, you know, provided as part of your deliverables. But can you say a little bit about sort of what it took for you guys to get ready to sort of produce all the artifacts that are required for like one release of your component?
Sure, that's an interesting topic because it's a long and interesting journey, and our product is evolving all the time. So at the beginning, Stargate ecosystem itself is a mono repo. So we just fork Stargate repo in our private namespace and then develop code on that repo. And then the Stargate team started to refactor the whole code base, and they extracted different components to different microservices, or you can call them images. Like the coordinator node becomes a standalone image, and depends on the user's needs, they may choose to install or not to install those optional services. If the user only wants DynamoDB compatibility, they only need to install our adapter as a container and the coordinator node.
I see.
Yeah, so now our product sits in a standalone repo, and we will donate the repo back to the Stargate community soon.
I see. Great. Very good. Hey, so Jeff, Tatu, do you guys have any questions for the team? Thanks for coming.
I have a quick comment and a question. So just to highlight the contribution that this team made, this was not by intent, but they ended up, Bakshwan just get hinted at it. We were going through a major architectural change to Stargate while they were working in parallel. This team ended up doing a lot of testing and actually finding multiple defects that we had in our setup of the new architecture. So in addition to contributing a whole new service, they made a material contribution to the bringing up the overall software quality of our release of Stargate V2.
Cool.
And my question is, the performance results that you showed were super interesting. There were some of them that were worse than I would have expected, and some that were better than I might have expected. Were there any surprises that you had in this data? And do you think that there's any maybe sort of low-hanging fruit or quick fixes that could be made to impact any of these performance numbers?
Good question. Do you have any thoughts?
Yeah, maybe I can talk about first and you guys can add up. It is surprising that the performance of delete item and get item, especially the delete item, is much worse than DynamoDB. We don't really know, but we want to point out that this is not a mature benchmark. We only run each query 10 times. So there can be some variation. And we can explain this put item latency. This is because of the schema difference we explained earlier. And that schema creation itself is expensive, and it can be amortized. And since we're only running it for 10 times, the schema creation overhead dominates. If we run it for 10,000 times, then we expect the performance to be much better. And for the query, our best guess as of now is that we're using a condition expression. This condition expression is a string literal, and we need to parse it. We are suspecting that DynamoDB actually caches the parsed results caches the binary code. And whenever they see a same condition expression, again, they just run that binary code, which will be much faster than what we are doing right now, because we have to parse this abstract syntax tree every time we see this condition expression.
Yeah, and for delete item, actually it's me to implemented that API. So when I was implementing that, actually the DynamoDB will require another parameter, which is called return value, which is to return the deleted record to the user. But as for the SDK that Cassandra provided to us, it does not have that parameter. So to handle that, I actually have to launch another query to get out the record that we want to delete and store it, and then put it in the return statement after the deletion. So it actually requires an additional query. So basically, for that part, that might be further optimized as long as that SDK is provided that additional parameter, so that we don't have to trigger another query.
Yeah, so this might be a low-hanging fruit.
Yes.
If we don't, if the delete item is executed in a eventual consistency mode, then we can actually fire the read query and the delete query at the same time in parallel. There are multiple things we can try around that.
Yeah.
And of course, the best solution would be to modify the Cassandra code and let it return the result before returning the deletion request.
Yes.
That's very interesting. Do you have anything, Tatsu?
No, I think I just echo what you said. It's like it's amazing that team was able to help us like with re-architecting and these performance results are interesting. Yes. So thank you.
All right, great job, guys. Looking
Well, we
forward
have
to
a
the final report.
So DynamoDB is extremely expensive.
Yeah, it is.
Can you do any cost terms of the savings of this approach? Because it seems to be one of the ways where Stargate, although it takes a longer time, many customers might be willing to pay that time for the improvement in cost.
Yeah.
I think actually last semester we made a mistake. We forgot to delete the tables just for
Yeah.
one night. It cost me like it cost us like
$300.
yeah $300.
Yeah. So did you think about, besides performance, to also do a cost comparison?
It's difficult to do a cost comparison because with Cassandra, you can either deploy it on cloud or on premise. And it's difficult to evaluate how much it would cost for an on-premise solution. And our solution is totally free.
Yeah.
And yeah, and as you said, DynamoDB is famous for its high cost. That's a good suggestion. We didn't quantitatively evaluate it, but we believe it will save a lot of cost. And also, most importantly, it avoids vendor lock-in for many users.
Yeah, so if you were to do a performance cost comparison on running Cassandra on AWS in a VM or a container, versus making these requests to DynamoDB for the same size tables, and say, sure, the latencies might be n times longer, but the performance cost comparison is significantly better.
Yeah,
Yeah.
definitely.
Yeah,
Yeah.
absolutely.
Very cool work. Well done.
Thank you.
Thank you.